Today, we're diving into the thrilling world of rStar-Math, where small language models are proving they can think big, literally. Instead of trying to solve everything at once, they break problems into smaller parts, check each step for accuracy, and improve over time. With innovations like Monte Carlo Tree Search and self-evolved deep thinking, rStar-Math is outshining giants like OpenAI's O1 preview and even GPT-4 on challenging math benchmarks. Let's dive in to see how it makes it.
All right, let's dive into something really cool today, how small language models, or SLMs, can master complex math reasoning. You might be thinking, wait, small models aren't the big ones like GPT-4, the ones that handle this stuff? Well, this paper, called rStar-Math, flips that idea on its head. It shows that smaller models can actually excel at math reasoning by using something called Monte Carlo Tree Search. Think of it as a smart way for the model to explore different steps in solving a problem, kind of like playing chess. It's not just about the final move, but about thinking through each step carefully. The paper introduces 3 big ideas. First, it generates tons of step-by-step reasoning examples to train the SLMs. Second, it evaluates the model's reasoning process, not just the final answer. And third, it uses a self-improvement loop where the model starts from scratch and gets better over time. The result? Smaller models can achieve results similar to much larger systems, all without relying on those big models for help. Let's break that down a bit. The rStar-Math system shows just how well small models can handle math tasks. After 4 rounds of refinement, using solutions generated from thousands of problems, the system performs strongly on various benchmarks. Check out how it does on the M8 benchmark, for instance. You'll see a significant accuracy boost, even passing some larger models. There's also an impressive result on the USA Math Olympiad. rStar-Math solves more than half of the problems, putting it among the top 20% of high-scoring high school students. You can look at the comparison table here to see how it stacks up against baselines like OpenAI's models. This method emphasizes iterative, deep reasoning instead of brute force or massive pre-training. Finally, the introduction sets the tone by describing System 2 thinking, more deliberate and methodical, where the model breaks down a problem, checks each step carefully, and then refines the solution until it's correct. Now, the key idea is how we train small language models to reason through math problems. It's not just about picking the right final answer. If any step in the chain of reasoning is flawed, the final answer can unravel. So, the system uses Monte Carlo Tree Search to look at multiple solution paths in stages. Look at Figure 1 here. Part A shows how the model generates various reasoning paths, assigns scores, and uses verifiers to choose the best path. In Part B, it ranks each step-by-step solution by quality, and Part C illustrates a multi-round training process where the model evolves using increasingly improved data. Generating such high-quality training data is challenging. Manual labeling is expensive and slow. Automated methods can be inaccurate. That's why rStar-Math leans on iterative self-refinement. But even with this, creating reliable data for math reasoning remains a difficult, ongoing task. Here, we get 3 big innovations. First, there's a unique data synthesis strategy involving Monte Carlo Tree Search, which produces these step-by-step reasoning paths, or trajectories. At each step, the model tries out potential solutions by running Python code and only keeps the ones that pass the tests. It then ranks these paths by scores, so we keep the solid ones and drop the faulty ones. Second, the process preference system comes into play. Instead of simply using a single score, this system compares different steps in pairs, giving higher rankings to more promising steps. This pairwise method helps reduce noise and errors in scoring. Lastly, we see a self-evolution mechanism. Same. Over 4 rounds of training on 747,000 math problems, the model and its scoring system both get better. Each round, it refines itself further, ultimately hitting high accuracy on future problems. This loop is critical to rStar-Math's strong performance. Next, let's look at how rStar-Math fares on multiple benchmarks. You might be curious if smaller models can really match bigger ones. According to these results, the answer is yes. For example, on the math benchmark, rStar-Math lifts some smaller models from around 58% accuracy to nearly 90%. That's a large improvement, and demonstrates the power of focusing on the reasoning steps. On more advanced tests, like the USA Math Olympiad, rStar-Math solves over half the problems. The authors also conduct experiments comparing their system against others, showing that their self-refinement approach and process preference methods lead to strong performance, especially on competition-level tasks. We then hear about how scaling the computation at test time and using reward models can increase the depth of a model's reasoning. The model can generate multiple solutions and select the best using a reward model. But this only works well if both the policy and the reward model are robust. rStar-Math addresses this by iteratively evolving them, enabling what the authors call System 2 reasoning. They also present the process preference reward model, which doesn't need dense step-by-step annotations. Instead, it uses pairwise rankings of intermediate steps. It's a lighter, yet more reliable, scoring approach. Finally, they tie all of this together with Monte Carlo Tree Search, letting the policy model and reward system work in harmony to break down complex math problems into manageable chunks. Now, what are the main challenges of training smaller models on math reasoning? Monte Carlo Tree Search assigns scores to intermediate steps, so you avoid the headache of manually grading every single step. Even GPT-4 can get stumped by Olympiad-level problems due to gaps in training data and the high cost of exploring all possible approaches. The authors propose using smaller models with a step-by-step reasoning approach and iterative training. They also introduce a code-augmented synthetic method with Monte Carlo Tree Search to build verified solution paths. That means each step is backed by actual Python code checks. In the end, there's a self-evolution process, letting both the policy and reward models improve in tackling more advanced math questions over time. This section dives into how to build those verified step-by-step reasoning paths. With Monte Carlo Tree Search, you form a solution tree where each node is a step with a quality score. The goal is to keep only the best paths. The system pairs each natural language explanation with Python code to make sure it's valid. If the Python code runs correctly for that step, it stays in the training data. Figure 2 here shows an example, matching natural language steps with Python snippets to ensure correctness. Next, we have a closer look at how Monte Carlo Tree Search explores possible solutions. It starts at a root node, then goes through selection, expansion, rollout, and backpropagation. Each path is a chain of intermediate steps, validated by Python code. Good nodes get a high Q value, indicating they're useful for reaching the correct final answer. A technique called upper confidence bounds for trees, UCT, helps the system balance between trying new paths and sticking to the promising ones. After enough rollouts, Q values become more accurate because the model sees which paths truly lead to correct solutions. At first, terminal-guided annotations assign scores only at the final step, but over time, the model learns to rate intermediate steps more precisely. This part outlines two ways of scoring reasoning steps. One is terminal-guided annotation, which only looks at correctness at the end of the entire solution. It's a start, but doesn't give much detail about intermediate steps. Then there's the process preference model, also known as PPM. It evaluates each step's potential to move toward a correct outcome. By checking partial paths, it gives more granular feedback and better training data. We also see how process reward models come into play. Traditional approaches might rely on human annotations or rough automated methods, but those can be costly or inconsistent. The paper suggests improving step scores by running big tree rollouts with PPMs, gradually refining them so they become both accurate and scalable. We now learn about the process preference model, or PPM, which scores math reasoning steps using a pairing strategy. Instead of giving each step a single rank, it pairs a step that leads to a correct final answer with one that doesn't, labeling them as positive or negative. This helps the PPM see which steps matter most for success, ignoring noise from the flawed ones. During training, these pairs come from the model's own exploration of solution paths. The PPM refines its understanding by comparing these pairs within a mathematical framework, ultimately giving us more accurate scoring for each intermediate step. There's also a method for filtering and improving these reasoning trajectories, especially for smaller models. The authors use a large math dataset and rely on Monte Carlo Tree Search to generate step-by-step solutions. Problems are sorted by difficulty: easy, medium, and hard, based on whether the solutions work. Hard problems get extra rollouts if the system can't solve them on the first pass, letting the model learn more. Then, the policy model is fine-tuned using the best trajectories. Meanwhile, the PPM steps in to score these solutions and guide future training. Across several self-evolution rounds, this approach gradually tackles tougher math questions with higher success. So how do these self-evolution rounds actually help smaller language models solve math? Take a look at Table 2 here, which shows accuracy across 4 rounds. We start with a bootstrap model called SLMR1 that relies on terminal-guided annotations alone. Each round builds on a stronger model and better data, refining both the policy and the preference model. The results? Accuracy jumps significantly, especially on Olympiad-level tasks. Table 3 also illustrates how each round surpasses the previous bootstrap baseline, highlighting the effectiveness of this iterative process. We see more details on the improvements in later rounds. In round 2, the system gains its first reliable reward model, refining Q values. Round 3 leverages PPM, augmented Monte Carlo Tree Search for better data quality, which helps the policy model tackle even more complex problems. Round 4 zeroes in on the hardest questions. Olympiad-level tasks. Additional rollouts and expansions boost coverage above 80%. Once they check the last unsolved problems, they find many are low quality, so they conclude the self-evolution here. By then, over 90% of the dataset is solved, showing significant coverage. Next, the paper details rStar-Math's performance on a broad range of benchmarks. These include math competitions, like the MAT benchmark, Olympiad problems, and out-of-domain tasks, like the Chinese college entrance exam. This variety ensures the system is tested on challenges of different difficulty levels. They experiment with models between 1.5 billion and 7 billion parameters. A full 4-round self-evolution process is applied to just one model, and the rest benefit from its data and refinements. Comparing results across these benchmarks shows how rStar-Math tackles tough problems without huge computational demands. To see how well rStar-Math does, they compare it to several baselines, including GPT-4 and other OpenAI models. Using pass-at-1 accuracy, we can measure if the model gets the answer on the first try. The numbers show rStar-Math substantially boosts smaller models, making them comparable or even better than bigger ones. On the math dataset, for instance, a 7 billion parameter model goes from about 58.8% accuracy to 90% thanks to rStar-Math. It also outperforms OpenAI's On1 Mini on some specialized benchmarks like AIME 2024. This indicates how small models, with carefully designed reasoning methods, can handle even advanced math tasks. Looking further, we see tables focused on pass-at-1 accuracy, where rStar-Math is compared directly against large language models like GPT-4. It often performs on par with or surpasses these state-of-the-art baselines. This applies to Olympiad problems, college-level math, and broader reasoning tasks. And Olympiad benchmarks. rStar-Math wins by a healthy margin despite using fewer parameters. By running 64 trajectories for in-depth reasoning, the model solves problems that typically challenge even the biggest systems. This shows how thorough exploration of solution paths can compensate for having fewer overall parameters. One key insight is that rStar-Math consistently outperforms larger models by scaling test-time computation with Monte Carlo Tree Search. Instead of brute forcing, it uses targeted exploration of multiple solution paths and then leans on its preference model to pick the best. It doesn't just do well on popular sets like MAT and GSM-8K. It also excels in Olympiad-level tasks and the Chinese college entrance exam. This demonstrates that a process of guided exploration plus stepwise preference modeling can handle a wide range of challenging math problems effectively. If you look at Figure 3 here, you'll see how rStar-Math scales performance by increasing the number of solution trajectories. Even with only 4 trajectories, it surpasses methods like best of n and comes close to higher-end models like O1 mini. As the number of solutions goes up, accuracy generally rises. However, on certain benchmarks like Olympiad tasks, it reaches a plateau around 64 trajectories, whereas for college math, it keeps improving more gradually. Then, there's an Ablation study checking the impact of rStar-Math's 3 core innovations on pass-at-1 accuracy. It shows how each piece, like self-refinement, the process preference system, and Monte Carlo Tree Search, adds to the overall boost in solving competitive and advanced-level problems. We also learn that self-evolution rounds boost rStar-Math's performance even further. Check out Table 5, which details the improvements from round to round. Once they introduce advanced reasoning and preference models, the accuracy jumps. By round 2, rStar-Math is already edging out GPT-4 in certain areas, and later rounds refine this difference. A big factor is the step-by-step verified reasoning trajectories, which decrease errors and expand the dataset with more difficult problems. Look at Table 7. It compares verified trajectories with methods like GPT distillation, random sampling, and rejection sampling. Verified trajectories come out on top, offering higher quality reasoning at each step. Here, Table 7 also highlights how step-by-step verified reasoning significantly improves model training. You'll see that these verified trajectories beat baselines like GPT-4 generated solutions and random sampling across various datasets. This holds true for easy tasks and more complex ones, showing that careful intermediate steps really matter for building reliable training data. There's also discussion about advanced reward models, such as PQM, which further optimize training. By using verified data at every stage, smaller models can reach higher accuracy on Olympiad and college math tasks. This reveals that you don't necessarily need huge amounts of compute if you have the right method and well-crafted data. Another interesting finding is the emergence of self-reflection in advanced reasoning models. It's been known that some large, closed-source models can spot and fix their own mistakes. What's new is seeing this kind of behavior in an open-source setting with Monte Carlo Tree Search-driven deep thinking. The model might start with a wrong approach, realize it's off track due to low scores, and then switch to a simpler strategy that leads to the correct answer. This self-correction happens naturally, without special prompts telling the model to reflect. It underscores how structured problem-solving methods can nudge models toward more reliable, introspective reasoning. An example of this self-reflection process appears here. The problem asks for the sum of 2 positive integers under a certain condition. The model first attempts a symbolic method but makes a mistake in the equation. Low scores flag the error. Then it switches gears to a straightforward brute force search, iterating through possible values until it verifies the condition directly. If you look at the figure here, you'll see each step and its corresponding score. The moment the model realizes its initial approach is flawed, it abandons it and picks a more reliable path. This is a prime illustration of how scoring can drive the model to correct itself on the fly. We also learn how policy and reward models both matter in System 2 deep thinking. Once the policy model is decent at generating solutions, the reward model becomes crucial in deciding which solutions survive. There's a figure comparing different model approaches, confirming that strong reward signals substantially increase accuracy. Notably, the PPM helps the system identify critical math theorems, like Fermat's Little theorem or the Pythagorean theorem. By giving these key steps higher scores, the model is guided to use them effectively, increasing its success rate on tougher math problems. Finally, the paper shows that rStar-Math's reasoning approach extends beyond typical word problems, hinting at potential uses in areas like theorem proving. In one example, it applies deep reasoning to a problem involving Fermat's Little theorem. For more general applications, the authors suggest a feedback loop to check if each reasoning path achieves the intended goal. All in all, rStar-Math demonstrates how smaller language models can reach strong levels of math reasoning. By generating high-quality training data and refining both policy and reward models through multiple rounds, it achieves solid results on demanding math benchmarks. Among its strengths are the ability to self-correct, and to spot crucial intermediate steps. Future work may involve exploring even more challenging problem sets, pushing this approach to higher levels of complexity. And there you have it, small models thinking big. Who knew that with the right training and a bit of iterative refinement, smaller language models could tackle math problems that even some of the largest models struggle with? It's a reminder that sometimes it's not about size, but about how you use what you've got. Thanks for diving into this with me.